Hey, AP Physics students, this is Mr. Evely talking to you. I am in Ohio right now with the robotics team, but I wanted to share with you the result of one of our problems. Okay, so one of the problems I had you do for today is number 84, and it's a pretty tough problem. It basically wants you to use the small angle approximation to figure out the angular frequency of this setup. Okay, not an easy thing to do. So I'd like to take you through it. The reason I want to do this is, like I mentioned before, there was something like this on the AP test years ago, and me being the somewhat cautious guy would like to share this with you. All right, so in 84, you have basically a bike wheel, which we're going to treat like a hoop. All right, and there's a wall back here to which we're going to attach a spring. Now, of course, this wheel has some spokes and things on it, so we can attach this spring to one of the spokes. And if somebody were to walk up to this and give it a little bit of a pull, rotate the tire or rotate the wheel a couple of degrees and let go, this is going to oscillate. All right. Now, it turns out then that this spring is going to get pulled out basically and snap back. Now, we're going to neglect the fact that this is going to be a slight rotation here. We're just going to say, hey, if the angle is small, this spring is going to stretch out a certain distance and want to snap back, and this will be the equilibrium position. Now, we know how springs work. The force is equal to negative kx, where x is the amount of compression or stretch. So if we're going to talk about this in terms of the rotation of the wheel, though, okay, we pull this thing out a little bit. Imagine that this angle here is theta in radians. Okay, now remember how this works. Theta in radians is x over r. X is this distance that we're pulling. Actually, it's this distance here. We're pulling the spring out. In the problem, they specify that the distance from the spring to the center is little r, and the distance or the full radius of the wheel is big R. So little r here, okay, this little distance is x, the distance we're pulling the spring. So instead of saying x, we could say theta times little r, okay? Now that means the force is equal to negative k theta r, okay? Now remember, when we did simple harmonic motion before, we said, okay, we got a block on a spring, F equals ma, says minus kx equals ma, and we solve basically for the acceleration. Okay, as long as the acceleration is equal to negative k over m times x, we could say, hey, if a is negative omega squared x, this guy is omega squared. Can we do the same thing here? Okay, now it turns out that we're going to have to talk about the torque created by this spring on this wheel. So if I say T equals I alpha, the torque is going to be negative K theta R times R. Okay, so it's the force times the distance from to the pivot point. Remember they said, hey, let's treat this like a thin hoop. Okay, so it's mr squared alpha. Okay, and if you want to be fancy, you can call it d squared theta dt squared. Or we can just solve for alpha and and say alpha is equal to negative k theta r squared, r times r, over mr squared. Okay? Now, theta then is the distance from equilibrium. This is the angular acceleration, so that means omega squared must be k r squared over m big R squared. So in other words, omega is r over r square root of k over m. All right, so it's not as terrible as we think. Again, we're using the small angle approximation. We're saying, okay, theta is really small, so we're not going to twist this around 90 degrees or anything. We're just going to let it bounce back and forth a degree or two. And we set up the equation for the acceleration, for the angular acceleration in this case. And we say, okay, well, if theta is the distance from equilibrium, then omega squared is all the constants that's left over. All right, and I'll let you solve the rest of the problem on your own. The second part of this is torsional pendulum. Now, a torsional pendulum is a pendulum that twists something around. So here I've got like a piece of plastic and a weight on the end, and if I turn it from equilibrium a little bit, it twists back and forth. Okay, there are some clocks that work on this movement. If you've ever seen an anniversary clock, it kind of does the same thing. All right, so here, basically, what we have, if I can find a nice piece of paper here for you, is some kind of massive disc, let's say, in this case, hung by a wire. And it turns out that we know how much torque it takes to twist this wire a certain number of radians. So again, in the linear world, when we have like simple harmonic oscillation of a block going back and forth, we say F equals negative kx. In this world, we're going to say the restoring torque is negative kappa theta. Okay, so kappa is kind of the torsional constant for that wire. It takes a certain amount of torque to turn it a certain number of radians. Okay, once again, back here we said F equals ma, so negative kx equals ma. And again, if you want to call this d squared x dt squared, knock yourself out, but it's just acceleration. And then we use that to figure out what omega is. If we apply the same thing here, we're going to say T equals I alpha. Okay, the torque is negative kappa theta equals the I of this object. I've made a disk here, but it could be a sphere or something else. And we're going to say d squared theta dt squared. Or acceleration, d squared theta dt squared is equal to negative kappa over I times theta. Meaning that if, remember in this case, A equals negative omega squared x, this is kind of like x. This is kind of like acceleration. This is omega squared. Without the negative sign, sorry. It's just kappa over I. So omega is kappa over I, take the square root. Which means the period of this thing is 2 pi square root of I over kappa. So in order to do this, you need to know the rotational or the torsional constant for this particular wire or band or whatever that is. You need to know the rotational inertia of the object you have on the end of it, and you can calculate the period, the frequency, and all that good jazz. Okay? So I hope this video helps. I hope that equation helps. And try a few of these on your own, and I'll be back on Monday to help.